Hello everyone, my name is Franz Mayer and I'll be presenting our work on the fly black box probably approximately correct checking of recurrent neural networks. My co-authors are Ramiro Vizca and Sergio Jovine, and this work was done in our affiliation, Universidad Uruguay, and is partially funded by ANI and ICT4B, which are both research agencies from our country, Uruguay. Just to give a brief overview of today's agenda, we'll talk about the motivation of our work, then specific context. I'll describe our approach, give some application examples, and finish with conclusions. Artificial intelligence is being used in areas such as health and cybersecurity, and the core problem with the state-of-the-art models is that they are opaque, non-intuitive, and difficult for people to understand. In order to be used in these areas, we need AI to be explainable and need rigorous methods for testing and correcting these models. We'll address this problem in the context of sequence classification. As an example, I will explain sequence classification in the context of log analysis, but sequence classification is a research area that is useful for many other areas such as sentiment analysis, genomic analysis, bank fraud, or malware detection. Here we have two sequences, one on the top representing normal behavior of a system and another one showing abnormal behavior. This could be a bug or some intrusion. The idea is to develop an intelligent system that is able to differentiate one from the other. And RNNs are a state-of-the-art technique for sequence classification. They are used as follows. From left to right, we begin with gathering training data that is processed by a learning process, and then you get an RNN that, when presented with a new sequence, it gives a verdict. For example, we may have this sequence presented to the network, and it may say, okay, this is abnormal with some probability. And this verdict is not easily understandable, as RNNs are complex, opaque models that have a continuous state space. In the case of an output, you end up you may end up with some questions. For example, you may have a user asking, why is this abnormal? Or you may have another scenario where some sequence is presented to the model, and for example, it is a clearly normal behavior, and the model may say otherwise. It may say this is abnormal, and a user may end up asking, well, what's wrong with the network? Because I see that it is clearly normal. So the goal of this work is as follows. We want to know if our model satisfies a property, and if not, explain why, so that we can analyze this error and pursue fixing the network. Here, satisfying or fulfilling the property means that the sequences that are classified as normal by the network belong to the property. In the context of the previous example, we may want to know if our network is able to detect some kind of bug, and this bug family may be specified in any way. It could even be a set of specific sequences defined by extension, for example. So for this, we have two possible approaches. The first one consists in inducing a model and then checking it against the property. So we have the network, then we induce a model out of it, and then we check this induced model. And this has two main drawbacks. The first one is that you need to specify the property in a way that it can be checked against the induced model, and if you find an error, this may be present in the induced model but not in the original RNN. The second possible approach is doing the verification on the fly, that is, extracting a model over the composition of the network with the property, which is both faster and avoids the drawbacks of the other option. In this work, we followed the second approach. So the idea is to induce a model of the intersection of the RNN and the complement of the property. This is done by treating this composition as a black box and inducing an explainable model out of it. In this case, the inducing model would be an automaton, and the general setting we propose for this is an active learning one, where we query the black box in order to model it. We want to model the error of the network in case it exists. So the idea would be to do PAC, probably approximately correct, black box active learning using the bounded L-star algorithm. This algorithm guarantees that a learner program can learn an automaton or a DFA by interacting with a teacher that exposes two interfaces. One of them being a membership query, which means answering yes or no to a sequence belonging to a target language, and an equivalence query, which means that the teacher is presented with a hypothesis, an automaton, and it is able to answer whether the proposed automaton is equivalent to the target black box or not. This way of approaching the problem does two things. First, it solves checking in a black box setting, and second, by not ever constructing a model of the system, we can say that it does it on the fly. So the idea here is to extract a simpler visual symbolic models representing the error of the network. So just to give a brief overview of how this algorithm works, it works in an iterative way, and what it does is it asks questions, it asks queries to the black box until it is able to build a model, an automaton. When it is able to do that, it builds an automaton and it asks an equivalence query to the teacher. And this is done until the equivalence is fulfilled or the proposed model is too complex. So this is done in an iterative way until one of these conditions is reached, and these conditions are reached. That's a guarantee of the algorithm. Now I will proceed to explain you how this comparison of models works, how this probably approximately correct comparison, this probably approximately correct equivalence, works. So this PAC equivalence, this is a framework that was proposed by Leslie Valiant, and I will quickly present it. This framework enables us to test whether two models are with some confidence good approximations. The confidence and the approximation are two parameters presented by delta and epsilon respectively, and we say that a model or hypothesis is an epsilon good approximation of another one if the probability of a randomly drawn element, for example one of these red elements that I present in the graph, the probability of a randomly drawn element being targeted differently by the two models is equal or lower than a given epsilon. And if we can say that with a confidence that is equal or higher than 1 minus delta, then we have two probably approximately correct models with epsilon and delta parameters. To test this, we randomly sample R elements, and if the R elements and the elements in this sample are targeted equally by the two models, which means both output are consistent, give a consistent classification for every sequence, then the test is passed. This is an example of a good test, a pass test, a test that passes this PAC equivalence test, and this is an example of a failed test, because there are some elements that are recognized as differently by both models. So this process of verification has two possible outcomes. Either the induced automaton is empty, meaning that the property holds with confidence at least 1 minus delta, or the automaton is non-empty, which means that the property is certainly false, and the automaton is an epsilon approximation of the error with confidence at least 1 minus delta. This automaton provides useful information for correcting the error in the network. How do we reach this point? Okay, if H is an empty automaton, the part on the left, it means that the probability of an element belonging to this football shaped gray area not being empty or having an element is smaller than epsilon. And on the other hand, if the induced automaton is H is non-empty, we can say that the intersection is non-empty, and this is guaranteed by the algorithm bounded L star. So we validated the practical interest of the approach in case studies of different application domains, and each one showcases different aspects of the problem. We tested on a cruise control system, on an e-commerce web app, on HDFS logs for recognizing normal and abnormal behavior, and on TATA box detection in DNA sequences. And in this presentation we will focus on the Hadoop file system logs and case study. This case study comes from the field of system security. Here we analyze the behavior of an RNN trained with logs of a Hadoop distributed file system. And in this example, there's no a priori characterization of the language of normal logs. Each log is preprocessed into a sequence of numeric symbols ranging from 0 to 28. And these logs were used to train an autoregressive model, a language model, that is, the output of the RNN is the conditional probability of the next symbol given all the previous ones. And this RNN, this recurrent neural network, can be used to build a sequence classifier in several ways. In this case, we use the RNN to predict the probability of a sequence. Then we compare that probability with a threshold, and the sequence is considered to be normal if it is greater than the threshold, or abnormal otherwise. And this classifier achieved an accuracy of over 98%, and there were no false positives. And having no false positives may be suspicious, maybe a suspicious outcome, and it is interesting. So that this is interesting to verify. So it is a case where we went ahead and verified some property. Some properties, more than one, but I will talk to you about one specific one. That is, we checked if the network learned to classify as abnormal sequences containing some specific set of symbols, and namely those not appearing in normal logs that we denoted A. And as a result, we obtained a DFA characterizing traces where the network failed to make a correct classification. And here we present a subgraph of the outcome. The experiment showed that on-the-fly checking exposed the fact that the RNN could actually incur in false positives, that is, predicting a sequence as normal when it is not, even if no such cases were found during training on a test dataset. And this output DFA depicts the error and helps understanding the logs where such misleading classifications occur. Keep in mind this is a subgraph of the output, but still here we can draw some conclusions out of it. Finally, and to summarize our contributions, we can say that we proposed an on-the-fly black box probably approximately correct checking of RNN techniques that avoid state explosion present in RNN model induction, that has no need for an external checker, and that the outputs provides an interpretable characterization of the errors as a DFA, and the technique was validated in a number of case studies. So that's it. Thank you for listening to me, and I will gladly hear your questions.